welcome to the lecture 8 in the series on noise control in mechanical systems, and I am Professor Sneha Singh from IIT Roorkee. So, today's lecture is we will solve some numerical problems related to the topic on propagation through medium boundaries. So, a quick review of the previous lecture, we had been able to derive the pressure deflection coefficient as Z2 minus Z1 divided by Z2 plus Z1, and the transmission coefficient, which is the pressure transmission coefficient, as 2 times of Z1 Z2 divided by Z2 plus Z1. And another relationship was 1 plus R is equal to T, and all these relationships were when the sound wave is incident normal to the planar boundary of the next medium. So, today let us solve some numericals related to that. So, the outline is that we will solve the numericals related to these concepts, which is reflection, transmission, absorption, acoustic impedance, and the transmission from medium 1 to medium 2 at the normal incidence. And we will also see some special cases of normal incidence at the medium boundary. So, let us see the first problem here. Calculate the absorption coefficient when the sound wave propagating in the air is being normally incident at the boundary of air and water for the following properties in SI unit. So, here we have from air it is travelling to water, and typically the speed of sound in water is much high and the density as well is much high. So, this is what is given to us. Let us calculate. So, to find out alpha, this is the relationship. So, we need to know the pressure reflection coefficient. R is Z2 minus Z1 divided by Z2 plus Z1. Here our medium 1 is air, because the sound is travelling in air, and the medium 2 is water. So, what happens? Z is simply rho C, which is the characteristic impedance. So, for Z2, Z2 would be 1480 into 1000, all of them in the SI unit. So, it is 1.48 into 10 to the power 6, and the Z1 for air. So, this is for water and this is for air. The Z1 comes out to be, it is going to be, if we see here the values, which is 1.25 and 346. So, 1.25 multiplied by 346, which comes out to be 432.5, both in the same SI unit. So, here you observe is that Z2 is of 10 times 10 to the power 6, whereas the Z1 is 10 to the power 2. So, the Z2 is here 4 times higher in the order of magnitude. So, Z2 is much higher in magnitude than Z1. If you try to calculate what overall, what you see is this is something like this. If you solve it, it will come very close to 1. This is the exact value you are getting. So, R is almost 1, we can say. So, this is a special case which we will be discussing very soon. So, here what happens is that when a sound is coming in contact and it is encountering the boundary of a medium which has a much higher impedance, if you find out the deflection coefficient, it is almost equal to 1, which means that whatever pressure is being incident, that same magnitude pressure is getting reflected back. And if you have this thing over here, you will see that T is also 2, very peculiar case which we will see. And if you try to solve for alpha, which is given in this question here, that you have to find out the absorption coefficient for this boundary, it should be 1 minus mod R square, which comes out to be 0. So, let us discuss about this special case where absorption has become 0, reflection coefficient is 1 and the transmission coefficient becomes 2, these 3 quantities over here. So, here this is the special case that we have encountered with this problem. Here what is happening, these are the two special cases which have similar result. Either the impedance of the next medium or medium 2 is much higher in magnitude compared to the impedance of the medium 1, or the impedance of medium 2 is infinity, which is extremely high impedance surface we are encountering. Then we see that R, which is equal to Z2 minus Z1 by Z2 plus Z1. If you solve it, let us divide the entire thing by Z2, we get this expression, and since Z2 is much higher than Z1 or Z2 tends to infinity, in both these cases this quantity here tends to 0, because the denominator is much higher compared to the numerator, it can be neglected. So, if we simply neglect this quantity here compared to 1, over here we have neglected this. So, what we are getting is that R simply becomes 1 by 1, which is 1, and T, which is equal to 1 plus R, becomes 2. Okay. Now, it seems quite a bit counterintuitive that the sound wave is being incident on a very hard or high impedance surface, and whatever the pressure wave is, it is incident on that same magnitude pressure wave or that same amplitude pressure wave is being reflected back, but at the same time, you know, intuitively we will think that okay, whatever sound is being incident, it is getting reflected back. So, there should not be any transmission, but that is not the case. The pressure of the transmitted wave or the amplitude of the pressure of the transmitted wave is almost twice that of the incident wave. So, it is doubling in magnitude, very peculiar. So, does that mean that, you know, suddenly we are creating new sound energy or suddenly something weird is happening? That is not the case. What happens here when this is this? Let us see and compare in terms of the sound energy and the intensities in the two medium. Okay. So, by the principle of conservation of energy, even at this particular interaction, the energy should be conserved. We are not generating suddenly a new energy. Okay. So, that means that the energy, total energy at the left side of the wall should be same as energy at the right side of the wall. Let us find out the intensity for these respective waves. So, the intensity of the transmitted wave is what? Let us find the intensity of the transmitted wave. It comes out to be the amplitude of the transmitted wave whole square divided by rho 2 C2, and the intensity of this incident wave comes out to be the amplitude of the incident wave whole square by rho 1 C1, because we are using this relationship that I is equal to rho C. So, if you see here, rho 2 C2 in this case is much higher in magnitude than rho 1 C1. So, overall, even if this PT max, now we know that PT max has almost doubled in magnitude compared to the PI max, because T is coming out to be 0, right. So, if we equate this, then what do we get? IT in terms of this, we get it as PI max square times 4, okay, from this particular relationship here, divided by rho 2 C2, which means 4 by some very large quantity. I am just going to write it as a very large quantity into I, because this here we get is rho 1 max whole square divided by rho 1 C1, and this is some very large quantity at the denominator. So, 4 divided by a very large quantity. So, ultimately what we get is that the intensity of the wave or the energy density, you can say, for the transmitted wave is actually much lower in magnitude. It is much lower in magnitude than the intensity of the incident wave. So, now this interaction makes more sense, that if we have a high impedance medium, although the amplitude of the pressure wave is increasing, but the intensity of sound actually decreases quite a bit in the high impedance medium. Let us see another special case, which is normal incidence at a surface of extremely low impedance. So, now it is just the reverse case of the previous one. So, from a high impedance suddenly we are going to an extremely low impedance medium. So, either Z2 is approximately 0 or Z1 is much higher in magnitude compared to Z2. So, in both these cases if you solve for R, which is Z2 minus Z1 by Z2 plus Z1, and if you solve it this way it becomes Z2 by Z1 minus 1 divided by Z2 by Z1 plus 1. Since Z1 is much higher in magnitude compared to Z2, so what are we getting here? Z2 by Z1 is much lower in magnitude than 1. So, essentially this term here, can be neglected compared to 1, okay, because of this particular relationship. Since we are neglecting this term, so what happens? R becomes minus 1 by 1 or simply minus 1, okay, and alpha is 1 minus mod of R whole square, which is 1 minus 1 whole square, which again is 0. And what do you think the transmission coefficient is going to be in this particular interaction? Once again you can use this relationship. So, 1 plus minus of 1, which should be 0. So, 0 transmission, okay. So, essentially what is happening is that when the wave is incident normally and from high impedance to a very low impedance medium is travelling, then there is a reflection, but there is the transmission coefficient is 0. So, physically what happens at this boundary? Let us say this is the boundary we are talking about. Let us say this is our incident wave, okay. That is our incident wave. Now, what do you mean by minus 1? Which means that the magnitude or the amplitude of the reflected wave is the same as the amplitude of the transmitted wave, but minus 1 indicates that wherever we have a peak of the incident wave, we are actually experiencing just the negative of the pressure, which means we are experiencing a trough in the reflected wave. So, the reflected wave should be something like this, just the negative of the incident wave. So, it should be like this. So, basically what is happening, the reflected wave is same as incident wave shifted by 180 degree in phase. So, because of the 180 degree shift, it is just the negative or the opposite of the transmitted wave in the waveform, where the amplitude remains the same. So, overall the pressure is cancelling each other out. You can see that the incident wave and the reflected wave together, when they are added or superimposed on each other, at every point in the space they are cancelling each other in the boundary. So, the pressure essentially at the boundary is becoming 0, and the pressure at the left hand side is 0, and same way the pressure at the right hand side becomes 0. So, by the continuity of pressure, this wave is flat, no wave at all. So, T equals to 0. So, this is a very favorable case. What is happening is that suppose we are travelling from a high impedance to a low impedance medium in terms of noise control in mechanical systems. If some such kind of interaction is encountered, what happens? We are able to bring down the transmission to 0. When this kind of, in an ideal situation, if this interaction is encountered, the transmission through that boundary becomes 0. So, the wave stops and does not penetrate into the new material, and at the surface the pressure also becomes 0 because the reflected wave cancels the incident wave. So, at the surface and near the surface in such interaction, the acoustic pressure becomes 0 near such boundary surfaces, which is a very favorable condition for noise control. Now, the third and the last case is that suppose the sound waves are incident at a fully absorbing surface, that is when the absorption coefficient of that surface is equal to 1. So, in that case alpha is 1 minus mod r square, and alpha itself is 1, which means that this mod r square is equal to 0. So, r would be 0. Okay. So, in that case r becomes 0, and if r is becoming 0, what does it mean for the impedances of these interactions? If you look at this relationship, if this is 0, this means that Z2 is same as Z1. Okay. This phenomenon is also called as impedance matching, which means that the impedance of the medium 1 and the medium 2, they completely match, and in that case T, which was 1 plus R, becomes 1. So, essentially what is happening here, if we again represent it through what actually happens at the boundary like we did in the very first case and the second case. So, what we see here is that, let us say this is our boundary, let us represent each thing with a different color. Okay. And we have an incident wave that is coming in at a certain kind of amplitude. There is no reflected wave because r is equal to 0, and the transmitted wave has the same magnitude and the same phase as the incident wave. So, essentially what you see is it behaves as if there is no medium change at all. Okay. In this phenomenon, because the impedance, the characteristic impedance of the two media are same, and we discussed this in the previous class that the characteristic impedance rho c, it sort of quantifies how resistant that medium is to sound wave propagation, and in this case, because the characteristic impedance of the two medium is same, it means that they both acoustically are same. They might be different on other parameters. We might have the medium which have different densities, they might have different bulk modulus, but overall the impedance becomes the same. So, acoustically for a sound wave, it behaves as if the medium is continuous in nature and there is no difference at all. Both are offering the same resistance, and hence the sound wave propagates through as if there is no change in the medium at all. Okay. Fine. So, this is the impedance matching case. Now, let us solve problem 2. So, the same as problem 1, in the problem 1 what happened was that sound wave was propagating from air and it was incident on the air water boundary, and the water had much higher impedance than air. Now, we reverse the case, it is propagating in water and then it is incident on the air. What is happening here? So, here Z1 has become 1.48 into 10 to the power 6 and Z2, so Z1 here is the water because it is travelling in water, and then it has to emerge out into air. So, air it is again the same way as we solved for a previous case, it is 432.5. So, here the reflection coefficient, so now this represents, you can see here itself that Z1 has become much greater in magnitude than Z2. So, this represents our second special case where R, which is Z2 minus Z1 by Z2 plus Z1, which is this quantity here. Okay. So, it is almost minus 0.999 as we had found for the previous case with a negative sign. So, approximately you can say R is minus 1. Okay. And what we have to find here, the absorption coefficient. So, alpha. So, once you know these special cases, you do not even need to solve them, because once you know that okay, one impedance is much higher in magnitude than the other, you see which special case is this, and you can directly come to the conclusion that the R is either minus 1 or it is plus 1. Okay. So, here in this case, if you know the special case, you can directly solve and say R is equal to minus 1 and alpha, which is 1 minus mod R square, is becoming 0. That is our answer. So, for both the problems, absorption is 0, but the nature of interaction is pretty different. Okay. Now, let us see a third problem in this situation. Here we have a sound wave of 0.5 pascals amplitude, normal incidence at the boundary between air and helium. Okay. Now, here it is not given whether it is propagating in air or in helium, but Suppose it is giving that the boundary is between air and helium and air is coming first. So, we assume that air is medium 1 and helium is the medium 2. Okay? And the characteristic impedance of the first medium is given to you and the characteristic impedance of the second medium is given. You have to find out what is the amplitude of reflected wave and transmitted wave and also the absorption coefficient of the boundary. Okay? So, let us solve this here. Let us first solve the reflection coefficient. Here medium 1 is air, medium 2 is helium. So, Z of 1 is rho 1 C1 which has already been given as 413. Okay. And the Z of 2 which is in helium is given to us as 170. So, this R can be which we solve as. Okay. So, let us solve for the first one. You have to find out the amplitude of reflected wave and transmitted wave. So, amplitude of reflected wave. Use the relationship of R which is PR max should be R times PI max and we are given the PI max which is 0.5. So, it is minus 0.417 multiplied by 0.5 pascals. This comes out to be minus 0.2084 pascals. So, what you observe here is that the pressure, the amplitude of the reflected wave has reduced and at the same time it has become negative. So, it is suffering from a 180 degree phase shift. Okay. So, the reflected wave is shifted 180 degree in phase from the incident wave and its amplitude has also decreased. So, even in this case when you add up the acoustic pressures in the interaction, so at the just the very left hand side of the boundary the reflected and the transmitted wave are coming together and the reflected wave is sort of subtracting or can nullifying the incident wave, but there is imperfect cancellation. So, an imperfect cancellation is happening. So, the pressure is going down, but it is not coming to 0. So, definitely there is some transmitted wave which we will find now. So, in the same way the amplitude of transmitted wave Pt max is T times of Pi max. So, this Pt max is, so T in this case, let us find out T first. 1 plus R is equal to T, R here is minus this thing. So, T becomes 1 minus of 0.2084. So, this comes out to be okay. So, R is not this minus 2.084, this is RR. Okay. So, let us just see this equation once again. It is 1 plus minus of 0.417 which is our R. Okay. And this comes out to be 0.583. So, Pt max should be 0.583 multiplied by 0.5 pascals. So, overall you get as 0.2915 pascals. Now, let us solve the last part of this question. the absorption coefficient of this boundary. So, alpha is 1 minus mod r whole square. So, 1 minus minus of 0.417 whole square, if you solve it, it comes out to be, which is a pretty high number. So, it is a high absorbing surface. Okay. The closer the alpha is to 1, the more is the absorption. Okay. So, with this I would like to close this lecture on the numerical problems for sound wave propagation at normal incidence. Thank you.